In 9.2, we talk about series and convergence. So if you remember in 9.1, we talked about sequences, specifically infinite sequences, where there were functions from the positive integers or sometimes the non-negative integers to infinity. Or excuse me, functions from positive integers to the real numbers. So now we're going to talk about series and convergence of series. So we start with what an infinite series is. Basically, an infinite series is an infinite summation. Now, I've ordered this first series starting at 1 and going to infinity. All right, so we start at 1 and go out to infinity. But notice it's just a sum of an infinite number of real numbers. So we can think of it as the sum of a sequence. So all of those sequences that we dealt with in 9.1, we're going to look at sums of those sequences. Now, the goal of an infinite series is to see if this sum, this infinite summation, actually adds up to a real number or if it does not add up to a real number. And once again, we're going to say the series converges if this sum adds up to a real number, and it diverges if the sum goes off to infinity or the sum simply does not exist. So we're going to look at a few approaches to dealing with a series. All right. Now, one thing you can start to do in order to find the sum of an infinite series is to take a look at what's called the partial sums. The partial sums are just what they sound like. They're the piecewise sums. So sum 1 is just the sum of the first term. Sum 2 is the sum of the first two terms of the series. Sum 3 is the sum of the first three terms, and so on and so forth. Sum number n is the sum of the first n terms of the series. And so what we can do is we can sort of get a pattern with what these partial sums are. And if we can see a pattern in the partial sums, maybe we can take the limit of those partial sums and see if in fact we get a real number. And that's really what convergence of an infinite series means. So we say an infinite series converges if the limit of the partial sums actually comes out to a real number. And if that's true, then we say the infinite series itself adds up to S. All right, the real number here we denoted by S. So that's really what it means to add up. Okay, so when I said earlier, we're going to see what this infinite series adds up to. What we really mean is a limit as n goes to infinity of these partial sums. So what does this series add up to? All right, and that's the terminology we'll use moving forward. So an infinite series converges if the partial sums have limit, which is a real number. And if that's true, then we say the series adds up to S, or the series is equal to S. And in the same vein, we say that the series diverges if and only if these partial sums diverge. All right. And by the way, diverge once again can mean going off, the limit goes off to infinity, or the limit does not exist. So if the partial sums diverge, then we say the series diverges as well. Now these next few sections are really focused on when does an infinite series converge, and when does that infinite series diverge? And so we're going to look at a few tricks to do that in the next few sections. The first thing we're going to do, however, is calculate the partial sums themselves. So let's take a look at this infinite series. The sum from 1 to infinity of 1 over 2 to the n. This infinite series is an infinite sum. If you plug in 1, you get a half. If you plug in 2, you get a fourth. If you plug in 3, you get an eighth, and so on and so forth. So you see we get 1 half plus 1 fourth plus 1 eighth plus 1 16th plus 1 32nd plus 1 64th, and so on and so forth. And so if we're looking at the partial sums, what you see is S1 is a half, and then S2, the sum of the first two terms, will be 1 half plus 1 fourth. Now, if you want to add those things together, that's 3 fourths. Hopefully that's not too much. 1 half plus 1 fourth is 3 fourths. S3, well, 1 half plus 1 fourth plus 1 eighth, or you could think of 3 fourths plus an eighth is going to be 7 eighths. And then you start seeing a pattern, hopefully, around S4 and S5. The fourth partial sum, well, just take the first three that we know that's 7 eighths and add a 16th. That is going to be 15 over 16. In a similar way, S5, the fifth partial sum, is going to be 31 32nds. Now, hopefully by now we start recognizing a pattern. We go 1 half, 3 fourths, 7 eighths, 15 over 16ths. And hopefully we see that the nth partial sum is always going to be a fraction, and that fraction in the denominator is going to be 2 to the nth power, and in the numerator it's going to be 1 less than that. So it's going to be 2n minus 1 over 2 to the nth power. 2 to the nth power minus 1 divided by 2 to the nth power. Now, what do we know about that partial sum? Well, we can take the limit of that partial sum. The limit of that partial sum you can find by either using L'Hopital's rule or just understanding that 2 to the nth power and 2 to the nth power are growing at the same speed. It turns out the limit of the nth partial sum is 1. There you go, I wrote that down here. So the limit of the nth partial sum, which is the limit of 2 to the nth power minus 1 over 2 to the n, is 1. Now notice that within doing this partial sums, we actually just came up with a sequence. And we found the function value formula for this sequence. The partial sums are themselves a sequence, in other words. So we found a sequence. That sequence is the sequence of partial sums. We came up with a function representation of the sequence of partial sums. And then we found the limit of that sequence. So what we've done here is we've said the limit of the partial sums is 1, and therefore what we can say is that this infinite series here, which is the infinite sum from 1 to infinity, 1 over 2 to the n, adds up to a finite number of 1. In other words, it converges to 1. All right? Now, by the way, there's kind of an interesting way to see that, another interesting way to see that this infinite summation has to add up to 1. And you can do this visually as well with this instance. It's kind of a unique situation. Usually we don't do this, but there is a geometric proof of this summation equaling 1 that you can go to. Let me look that up for you. All right, so this is what I did. I took this is something you can find on Wikipedia, the infinite summation. And what you see here, this is the drawing I was referring to. We have this square, which is 1 unit by 1 unit. If I cut the square in half, what that leaves me is a half on the left-hand side, and then on the right-hand side, this half is going to be subdivided. So what I do is then I cut the right-hand side in half. What do you get? 1/2 and then 1/4. You get the first 2 terms of that infinite series. And then you cut the square and you cut the remainder in half again. Well, half of the remainder is 1/8. You cut the remainder in half again. That's 1/16. You cut the remainder in half again. That's 1/32. And so you can keep doing this to infinity. Cut in half, you get 1/64. If I'd cut in half again, I'd get 1 over 128. If I'd cut in half again, I'd get 1 over 256. And you can just continually cut in half and cut in half and cut in half and keep adding these fractions up. And you can see that if you do this an quote infinite number of times, you get the entire square. All right. And the entire square, remember, is a 1 by 1 square, so it's 1 square unit. So that's kind of an interesting situation in this case. This is the way to prove it mathematically. The other way is kind of just a neat visualization. All right. Now, obviously, this is not the only infinite series. Whoops. We can have other infinite series as well. Here's one. Take an infinite sum of 0.4 from n equals 1 to infinity. So let's take a look at that one. So here we are, take summation of 0.4. By the way, when you don't see an n here in the argument, what that just means is you're getting 0.4 and then 0.4 again and 0.4 again. So we're taking 0.4 plus 0.4 plus 0.4 and so on and so on and so forth. So the first partial sum is going to be 0.4. The second partial sum, the first 2 terms, 0.4 plus 0.4 adds to 0.8. The third partial sum, we're just going to take that 0.8 and add another 0.4, so that's 1.2. The fourth partial sum, 1.6. Notice that each time we're just adding 0.4. 2.0, S5 was 2.0, S6 would be 2.4. And now that I have the first few terms of the partial sum sequence, I can write out the function for it. It's going to be just 0.4 times n. Now we're trying to find, remember, the infinite series, which means we look at this sequence and we take the limit as n goes to infinity. So the limit of 0.4 times n as n goes to infinity is in fact infinity. All right. As n gets bigger and bigger and bigger, this sequence, just the terms in the sequence just get bigger and bigger and bigger, and therefore it goes off to infinity. So what we say is that this summation, this infinite series, diverges, or some people would say equals to infinity. I'm going to say diverges to oops, to infinity. All right, so there we go. Diverges to infinity. By the way, we should have expected that. This example shows us that if we just have the same number over and over and over and over again added up, obviously this sum is going to grow like crazy. So one of the requirements of this sum actually adding up to a real number is that these individual terms have to get smaller if I ever want this sum to add up. And that's what the next slide on the PowerPoint actually shows us. The next slide gives us what's called the divergence rule. So it says if a sequence doesn't actually get close to zero, then adding that sequence up is never going to give us a convergence idea. In other words, if the limit of the underlying sequence is not zero, then this infinite summation has to diverge. Okay? Again, notice that we're talking about the underlying sequence. It's the sequence that's getting added up here. So if it doesn't go to zero, then there's no way that this summation, can converge. It has to diverge. All right, so that's what we saw in that example. Now, a couple of things that we're going to look at in the next few slides is we're going to develop some shortcut rules. That's what basically the middle part of chapter 9 is all about. It's trying to determine whether a series converges or diverges based on some shortcut rules that we can develop. So let's start looking at some specific examples of types of different series. So let's calculate the first few partial sums of this series and see if this one converges or not. By the way, this is a special type of series called a telescoping series. We'll see why that is once we start out writing the first few partial sums. So I want you to just push pause on the video and just write out, if n equals 1, we get 1 over 1 minus 1/3. So write out the first few terms of this series and see what you get. And then we'll do the partial sums together. But push pause, write out the first few terms of this series, and take a look at it. All right, so hopefully you went ahead and did that. If you did that, you plug in 1, you get 1 over 1 minus 1/3. If you plug in 2, you get 1/2 minus 1/4. If you plug in 3, you get 1/3 minus 1/5. If you plug in 4, you get 1/4 minus 1/6. If you plug in 5, you get 1/5 minus 1/7. Now, as you can see, we're going to add up all these terms, right? So let's do first partial sum. First partial sum is just this first term here, 1 over 1 minus 1/3. Now, I'm going to keep it as 1 over 1 minus 1/3 for reasons that you'll see in just a moment. The second partial sum, we're going to add these up. Now, I'm going to do this. I'm going to say 1 over 1 plus 1/2 minus 1/3 minus 1/4. All right, 1 over 1 plus 1/2 minus 1/3 minus 1/4. Now, in the third partial sum is where things start to get interesting. So we're looking at the first 3 terms. And this is the reason it's called telescoping. So here's what's going to happen. notice we have a minus 1/3 here, and we have a plus 1/3 here. So when I add up the first 3 terms, this minus 1/3 is going to cancel out with the positive 1/3 here. And so this sequence telescopes, in a sense, gets, again, think of a telescope. You expand and contract this looking glass. And it goes from 6 terms down to 4. And if you notice what those 4 terms are, they're 1 over 1 plus 1/2 minus 1/4 minus 1/5. All right, let me scroll up a little bit. So I get the first 2 terms stay the same, 1 plus 1/2. And then the next 2, now we get minus 1/4 and minus 1/5. Now, what if we add a 4th term? So we start here, 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 here. Well, I have 8 little pieces, 1 over 1, minus 1/3, 1/2, minus 1/4, 1/3, minus 1/5, plus 1/4, minus 1/6. The 1/3 and the minus 1/3 are still going to cancel out. But now notice that there exists this minus 1/4 and this positive 1/4 that will also cancel out. So we get a positive 1/4 and a minus 1/4. Those are going to cancel each other out. So we go from 8 terms down to 4, telescopes down to 4, and notice what those terms are. 1 over 1 plus 1/2 minus 1/5 minus 1/6. Let's do one more term. Add in the first 5 terms here. Well, everything goes the same, but now this minus 1/5, I know that's really light on purpose, is going to get canceled out with this positive 1/5. And so, again, the only remaining terms, 1 over 1, 1/2, now minus 1/6 minus 1/7. And you can imagine that if you add another term, you're going to get rid of the 1/6. If you add another term, you're going to get rid of the 1/7. So this 5th partial sum looks like that. And now we can see the pattern. The pattern of this telescoping series is we always start with 1 over 1 plus 1/2. And then you do minus 1 over n plus 1, n plus 1 specifically in the denominator, and then a minus 1 over n plus 2 in the denominator. Now, if you take the limit of that thing, that's the limit of, 1.5, that's what you get when you add 1 plus 1/2, minus 1 over n plus 1, minus 1 over n plus 2. Sorry, we're a little bit down there at the bottom. So limit of that whole thing. Don't forget this is the limit of that whole deal. So the limit of 1.5 just comes out to 1.5. If you do the limit of 1 over n plus 1 as n goes to infinity, denominator gets really big, this whole fraction goes to 0. And as n goes to infinity, this whole fraction also goes to 0. So the limit is 1.5 or 1.5. So this infinite summation converges to 1.5. Okay, if you want to write that as 1.5, if you want to write that as 1.5, either way is all right. So again, that's a unique situation in that it's telescoping, that essentially as we start going, this 1/3 gets canceled out with this 1/3. Then the next step, this 1/4 gets canceled out with this 1/4. 1/5 gets canceled out with this 1/5. And if you kept going, again, 1/6 would be canceled out with a 1/6 over here. A 1/7 would be canceled out with a 1/7 over here, and so on and so forth. So all that remains are essentially these first two terms plus some stuff that's going towards 0. All right, so that is the idea of a telescoping series. Okay. Now the next type of infinite series that we're going to look at is a geometric series. Now a geometric series has a property that says 7 times 1/4 to the n. Basically, we have an exponential piece that's being raised, an exponential. In this case, we have our base being 1/4 being raised to the nth power times a coefficient out front. Apologize. I just caught that I started my count at 1. It turns out with geometric series, a lot of times I want to start my count at 0. So here's what I'm going to do. Instead of starting my count at 1, I'm going to start my count at 0. Okay, and we're going to see how this comes into play. We're going to find some partial sums, and we're going to look at how this thing adds up. All right. But notice that I did put this at n equals 0 to start with. Okay, that is important in geometric series. We'll see what happens if we don't start it at 0 in a second. But again, with geometric series, it's easiest if we start at 0. So here's our geometric series. 7 times 1/4 to the n added up from 0 to infinity. Now, if you plug in 0, 1/4 to the 0 power is just 1. So you get 7 times 1. If, whoops, maybe there we go. So 7 times 1. If I plug in n equals 1, you get 7 times 1/4. If you plug in n equals 2, obviously you do the exponents first. 4 times 4 is 16, so you get 7 times 1/16. If you plug in 3, you get 7 times 1/64. Now to make it easy, my partial sums, I'm going to start with s sub 0 so that you can see that it's just 7 times 1. By the way, I'm writing that 7 out there on purpose. I'm not multiplying in on purpose right now. If I look at my first partial sum, I'm going to look at the 0 term and the 1 term. So 7 times 1 plus 7 times 1/4. Okay. Now, notice these 7s I can factor out if I'd like. So what I could do is factor out the 7 and do 1 plus 1/4 in here. Now, in this case, we're not going to see a very nice pattern with my fractions, with writing these things as fractions. So let's actually write these things as decimals, and then we'll round to a few places. So 1 plus 1/4 as a decimal is 1.25. Okay. If I add a 16th times 7 to that, well, that's just like adding a 16th to 1.25. So if you add a 16th to 1.25, you get 1.3125. If I add in a fourth term, that's like adding 1/64th to this 1.3125 number. So let's take that and add 1/64th to it. What you end up with is obviously 7 times 1.328125. What's going to happen if I add 1 over 256 times 7 to this? Well, that's just like adding 1 over 256 to this number. So we end up with 7 times, add 1 over 256, you get 1.332, et cetera, et cetera, et cetera. My calculator gives me out 332.03125. Well, now let's add one more term, add 1 over 1024. You end up with 7 times 1.333007813. You add on another term. Add on 1 over 4096. You get 1.333251953. Now, the SN doesn't really have a good pattern here. It's not a good fractional pattern by any means. So we probably don't have a really good function that we can create for the nth term of this sequence. Not one that's really easy to see anyways. However, we can still look at the numerical pattern that we've established, and we can see that as this keeps getting bigger, what this looks like is that Sn is approaching 7 times 1.3 repeating. So Sn, as n goes to infinity, even though I don't have a function for it, looks like 7 times 1.3 repeating. Let me make sure I write that repeating symbol there. So 1.3 repeating, which, by the way, is 7 multiplied times the fraction 4/3. Okay? So what's happening here is that this infinite sum is 7 times 4/3. So it does, and whoops, in fact, this infinite sum does in fact converge, let's move this down, to 7 4/3. Now you might say, well, wow, how can we get that? Are we going to have to really know fractions well? Because each time, obviously, if we start with something other than 1/4, it's not going to end up with 1.3 repeating. If we started with, for instance, 2/9, like we will in the next problem, what are we going to get? And it turns out that this example is a geometric series. And so it has a very particular pattern. Notice that 4/3, how that plays out with 1/4. First off, the 7, obviously, we could have just factored that out at the very beginning. The really interesting part is an infinite sum of 1/4 to the nth power. And what's 4/3? How does 4/3 and 1/4 go together? Well, if you think about 1 minus a fourth, 1 minus a fourth, Let me go through this. 1 minus a fourth is 3/4. 4/3 is the reciprocal of 3/4. So what you could do is you could say, oh, we're talking about multiplying by the reciprocal of 3/4. That's also known as dividing by 3/4. So that 3/4 comes from dividing, or excuse me, that 3/4 comes from doing a division of 1 over 4/3, or taking the reciprocal of 3/4. So reciprocal of 3/4 is 4/3. Reciprocal of 4/3 is 3/4. That's the connection there. All right. And that says this better in this slide here. So if we have a geometric series, now again, a geometric series is always one where we start with a constant times some r to the nth power. If that r is between -1 and 1, then this underlying sequence is going to go to 0. We mentioned that last time. And therefore, it's always going to sum up to a. Now this says divide by 1 minus r. That's like multiplying times the reciprocal of 1 minus r. So the way it's written is, if r is between -1 and 1, then this infinite series is going to converge, and it's going to converge to a over 1 minus r. Now, if r is bigger than 1, then this underlying sequence here goes off to infinity. So obviously this thing diverges if r is bigger than 1. So if r is between -1 and 1, then underlying sequence goes to 0, and the series, the infinite sum, goes to a over 1 minus r. If r is bigger than 1, then this thing diverges. Goes off to infinity, or it jumps back and forth between positive and negatives, and then it just diverges in a different way. All right? So this is the rule for geometric series. All we have to do is see that that base is less than 1 in terms of absolute value, and then we can apply a over 1 minus r. If that base is bigger than 1 or equal to 1 in absolute value, then we know the infinite series diverges. So let's take a look at this example. Example 5a. We have an infinite series, which is the sum. Now notice that once again our sum starts at 0, goes out to infinity, of 5 times 2/9 to the nth power. Now this thing is a geometric series because we have a base raised to the nth power, and then I have this times this coefficient here of 5. So infinite series, which is a geometric series. I look back on my formula and I see, oh, the base is between -1 and 1. It's less than 1 in absolute value. So I know that that infinite series that starts at 0 is simply going to be a over 1 minus r. So if I take this, now that I know that fact of infinite geometric series, I can simply apply that rule, that geometric rule, and come up with it. Come up with the sum. We're saying, since r is equal to 2/9, that's a number between -1 and 1. All we have to do is write a over 1 minus r, which in this case is 5 over 1 minus 2/9, which is 5 divided by the fraction 7/9. Be careful when you divide a fraction of 7/9. Make sure you put that in parentheses. So when you type that into your calculator, which is 45/7 as an improper fraction. So there you go, 45/7, which is whoops, excuse me, 6 3/7 if you'd rather write it as a mixed number. I like writing this as 45/7. So because we know it's geometric, we can simply apply that rule, and we know that this summation is equal to 45/7, and therefore this converges. All right, and that's it. By the way, you may be asking yourself why this geometric rule always has to be true. Why is it that anytime r is between -1 and 1, why do we get this weird summation? Let me go through why that is, why we get that summation. I'll do it fairly quickly, but I'll show you why this always works. Let's go over to this sheet and explain that. So think about a times r to the n. Now, again, the a part is not that big of a deal. You can factor that out. So that's kind of just a coefficient. You can factor that out and all that kind of stuff, as we've seen. So the real interesting part is, why does the sum of r to the n add up to 1 over 1 minus r, right? So again, factoring out the a on both cases. And it's actually just based off of polynomial division. So if you think about it, take the polynomial 1 minus x to the nth. Now this n could be 4, 5, 6, doesn't matter, and divide it by 1 minus x. Well, when you do that, you could have also taken x to the n minus 1 and divided by x minus 1. That's just multiplying top and bottom by a -1. Now, if you go and do a long division on x to the n minus 1 over x minus 1, you end up with x to the n minus 1 plus x to the n minus 2 plus x to the n minus 3, and so on and so forth until you get down to x squared plus x to the first plus 1. All right? So what you see here is that the sum of the first, starting at power 0, again, 1 is x to the 0 power. This is x to the first, x squared, and so on and so forth, up till you get to x to the n minus 1. The sum of that can be simply written as 1 minus x to the n over 1 minus x. Now that works for any value of n, which is a positive integer. And when you take the limit as n goes to infinity, let's take the limit as n goes to infinity. We've done this before. And going to infinity. Of that thing, well, depending on what my base is, if my base of x is a number which is smaller than 1 in absolute value, then this thing, x to the n, as n goes to infinity, is simply going to go to 0. If, as n goes to infinity, this x is a number which is bigger than 1, then this thing goes off to infinity. So this thing goes to 0 when x is small. this thing goes to infinity when x is big. All right, small, big compared to 1. So if it's going towards 0, then we end up with simply 1 over 1 minus x. If it goes to infinity, then we end up with this equaling infinity. And so if you replace the letter x with the letter r, you get exactly what this geometric sequence does. So it's basically just polynomial division with a limit as n goes to infinity. All right, so that's what this geometric series rule is actually doing for you. But it turns out that's really nice because, as you can see, we can deal with any geometric sequence, any geometric series starting with an n equals 1 to, not n equals 1, n equals 0 to infinity, and get a nice short answer. Now, the trouble lies when we don't want to start at 0. What if we want to start our summation at 1 instead of 0? Now, the geometric series rule, this summation always starts at 0. But if it doesn't start at 0, we can still use this rule and just utilize it in a slightly different way. Okay, so we just need to use a little bit of algebra if our summation does not start at 1. Let me give you an example of what I mean by that. We just found out that based on the geometric series, when you take an infinite sum from 0 to infinity of 5 times 2 ninths to the nth power, you get 45 sevenths, or 6 3/7 if you'd rather. But also, what this sum is just a bunch of terms. We started our count at 0. So our first term was 5 times 2 ninths to the 0 power. And then we were going to add 5 times 2 ninths to the first power. And then we were going to add 5 times 2 ninths to the second power, and so on and so forth until we go out to infinity. Well, what if I truncate these terms and sum those out to infinity? Well, it's pretty clear that this is actually the sum of 5 times 2 ninths to the nth from 1 to infinity. So in other words, if I don't start at 0, if I don't start my sum at 0, this sum is embedded inside of the summation from 0 to infinity. Now, by the way, 5 times 2 ninths to the 0th power is just 5. But what we know now, since this sum from 0 to infinity is 45 sevenths, then, whoops, my apologies, then this thing has to be 45 sevenths. Again, we said 5 times 2 ninths to the 0 is just 5. So all we have to do now is subtract 5 from both sides. So take 45 sevenths, subtract 5, and what you get as an improper fraction is 10 sevenths. So this summation here, subtracting 5 from both sides, you end up with 10 sevenths. Okay, that's the way I like to do it. Some people memorize other formulas when you start at 1. I just say, oh, well, when you start at 1, you just think about the 0 term plus starting at 1. We know what what happens when you start at the 0 term. That's just that geometric series rule. So just subtract that first term from both sides, and we end up with the right number here. Okay. By the way, you can do that if you started your summation at n equals 2, you just have to take the first two terms and subtract the first two terms from both sides. But there you go. So n equals 1 to infinity we can do because we know the rule for n equals 0 to infinity. All right, so here's what I'd like you to do. I'd like you to try example 6a. Example 6a says find the infinite series of 6 over 2 to the nth power. And that series starts the sum at 0 and goes out to infinity. Once you do that, I want you to also try example 6b, which says, well, now that after you found the infinite series starting at 0, now go ahead and find the infinite series starting at 2. So find the infinite sum, n equals 0 to infinity, and then also find the infinite sum, n equals 2 to infinity, of 6 over 2 to the nth power. So go ahead and push pause on the video. In about 5 seconds, I'm going to start back up. All right, so the first thing we have to do, first, again, try it if you haven't tried it before. We're starting. I'm going to show you how to do it. So 6 over 2 to the n. So first off, this doesn't exactly look like a times r to the n, but it can be written as a times r to the n if I simply put 6 times 1/2 to the nth power. So notice that that is the same thing. The 6 has no exponent, so you can take that out. That's the coefficient out front. And then when you're dividing by 2 to the n, that's like doing a 1/2 to the nth power. So if you rewrite it like that, then it does, in fact, look like the geometric series that we've been dealing with. And that geometric series obviously has r of 1/2. And so it is going to converge. So I can use my trick of, I shouldn't say trick, my algebraic calculation formula of saying, let's take a over 1 minus r. In this case, that's 6 divided by 1 minus 1/2, which when you go and calculate the whole thing, you end up with a 12. All right, so 6 divided by 1/2 is a 12. All right, 1 minus 1/2 is 1/2, obviously. So this thing converges, this summation converges to 12. Okay. Now, what if we started our count at n equals 2, like on part B? Well, we have to think about this. When you start at 0, if I would have plugged in 0, I would have gotten 6 divided by 2 to the 0 power. If I had plugged in n equals 1, I would have gotten 6 over 2 to the first power. And then the rest of it would have plugged in the second power, the third power, the fourth power, n equals 2. So the summation from 0 to infinity can be broken down as what I'll call the 0 term of the underlying sequence is 6 times over 2 to the 0. The second term is 6 over 2 to the 1, and then the summation that I want. So I know that specifically this piece here, I'm going to cut and paste, n equals 0 to infinity. We just calculated that as 12. 6 over 2 to the 0 is just 6. 6 over 2 to the 1 is actually 3. So that's 6 and 3. We'd subtract 9 from both sides. And what we get is that the summation that I'm looking for is 3. All right, again, subtract 9 here because 6 plus 3 is 9. Subtract 9 here, you get 3. So there you go. The sum from 2 to infinity is 3. By the way, this also shows, that if the sum from 0 to infinity converges, then the sum from any number to infinity also has to converge, right? You probably caught that earlier, but just to point that out specifically. So that's how you do that. Now let's do one more of these. Let's do example 7 here. Infinite sum from 0 to infinity of 5 times 1.2 to the nth power. Go ahead and push pause on the video and do your calculations here. Hopefully you went ahead and did that, and hopefully you caught what was going on there. We have 5 times 1.2 to the nth power. The r inside is 1.2. That r is greater than 1, and so all we have to do is go back to our geometric property and say that must diverge. So the infinite sum has to diverge because this underlying 1.2 to the n, each term in this infinite series, when you add them up, is going to get bigger and bigger and bigger, and so you're going to add up, and it's going to go to infinity. All right, each term in the underlying sequence gets bigger and bigger and bigger, and therefore we diverge. Okay, that one's a little bit tricky because you're used to doing this a over 1 minus r every time, but remember, a over 1 minus r only works when r is between -1 and 1, right? So when r is between -1 and 1, and we have a geometric series, then we can use this special formula. If r is bigger than 1 in terms of absolute value, then when you have this series, it has to diverge. So geometric series are a very special type of series. Obviously, not every series that we're going to look at is going to be geometric. And so the rest of the middle part of chapter 9 is going to be devoted to saying, well, what about other series? We know geometric series, when they diverge and when they converge. We saw telescoping series. We saw that if the underlying sequence doesn't go to 0, then the series has to diverge. But there's a number of other rules too. It turns out sometimes when the underlying sequence goes to 0, this sum converges, and sometimes when that underlying sequence goes to 0, this sum diverges. And so we're going to look at that in the next sections. So for this section, you should know geometric series really well. That's going to come up over and over and over again in the next few sections. All right, so that is it for section 9.2.